Okay, welcome back to the online causal inference seminar. I hope you all had a great summer. Today we're excited to have Anish Agarwal from Columbia University. We'll talk about synthetic combinations, a causal inference framework for combinatorial interventions. After that, we'll have a discussion by Christina Liu from Cornell University. Today we also have a collaborator of Anish in Q&A. So Binet Agarwal is also in Q&A. So as usual, feel free to be encouraged to post your question in Q&A, and Abinet will handle them. Okay, thank you all for coming. Without further ado, Anish, feel free to get started.
Perfect. Can you see my screen? Perfect. Okay, so hi everyone. My name is Anish Agarwal. Thank you all for coming to this talk. Today I'll be talking about synthetic combinations, causal inference framework for combinatorial interventions. This is joint work with Abhineet and Suhas. I met Suhas at MIT, and Abhineet's a PhD student at Berkeley. So please ask Abhineet questions along the way. So in causal inference, a key framing question is, what will happen to Y if we do A? Right? So Y is some outcome of interest, and A is some action or intervention that you can take. In practice, a lot of times what I found is what you really care about is combinatorial interventions, right? So what that means is something like, what will happen to Y if we take a combination of actions, right? And so what are examples of this where you take combinations of actions? Suppose you are Netflix, you may ask the question of what will happen to a user's engagement level if they're recommended a new combination of movies, right? Normally, when we think about the recommendation system problem, we think about you recommending a single item. But normally what you're doing is recommending a collection of items. That's exactly what you all face, what we all see when we go to any sort of movie streaming platform. It shows up in other places, say in medicine, you have things like what will happen to a patient's disease status if we knock down a different combination of genes, right? So here the outcome is the disease status. The intervention is which combination of genes you knocked out. Say in machine learning, what will happen to prediction performance if we select different combination of features, right? And things like, so as you're doing feature selection, this is a typical problem that shows up, right? And so in all of these things, the crucial question we want to understand is, what's the causal effect of different combinations on your outcome Y? So, and over time, what we're seeing, especially in practice, is we want to go more and more personalized with our interventions, right? We want to have a highly personalized experience for each person or each individual on a platform. And this is getting especially exacerbated with generative AI, where, you know, n is equaling to 1 when we think about experimentation and experiences that different people have. Right. Now, what is the challenge when we think about combinations with respect to personalized outcomes? One is that if you have p combinations of things, there's a combinatorial number of experiments you need to run to actually figure out the causal effect of every particular combination, right? And the second is that if you're in the observational setting and you can't run an experiment, you typically have insufficient data and unobserved confounding that you have to then wrestle with. So let me just try to set up the problem through the lens of recommendations, and let's just worry about even the experimental challenge, right? So suppose there's Abhineet, he's an individual, and I want to know what would his rating be? How much time would he spend on, say, Netflix if he recommended this combination of movies, which is Harry Potter, Transformers, and I forgot the last one. And so I need to run the experiment, say, to actually give them this combination and see what was his engagement level if he came on Netflix. Right. Now, let's say I want to know this for both myself and Suhas and everyone else on the system. Right now, I have a lot of users. I need to figure out what the engagement level for them would be under this combination. So let's say there's n users. I need to figure out what is the thing under all of them. And say in total, I have p different movies that I'd like to recommend. And I want to recommend any combination thereof. Right. So if you have p different movies and I want to figure out what is the engagement level if I recommend them any particular subset of movies, there's 2 to the p combinations. Right, so that's a very, very large number of combinations I want to potentially figure out if I want to build a highly personalized recommendation system, right? And so running all of these n, which is the number of users, times 2 to the p experiments is going to be infeasible, right? Why? Because n is going to be large, and p, even for moderately large p, you just have this explosion of the number of possible combinations, right? So one question we'll look at, and we'll actually answer it right at the end of this talk, is can we design a data efficient experiment to recover all n times 2 to the p entries with far less observations? Okay, and the answer will be really at the end of this entire talk. Now, in the observational challenge, where you don't get to decide what people watch, they just watch what they watch. This is probably the way your data is going to look like, right? So this is your observed engagement level for that particular user and combination. Now, and you can now think of this as a matrix completion problem, right? That's where matrix completion got its roots from, is this kind of recommendation system problems called the Netflix challenge many years ago. Now, when you're trying to recommend combinations of movies, a fundamental problem you're going to hit, and we see this, we will show that in an empirical study we do, is that most combinations are completely unobserved, right? So for most combinations, you have 0 entries available. That is, there are no users that have rated that combination of movies, right? And so matrix completion is just not going to work because you just have no data for those columns, right? So again, the question comes in this observational setting is, can we recover all n times 2 to the p entries, even if we don't observe most combinations? Okay. So that's really what this talk is about, is a causal framework for personalized combinatorial interventions. Okay. So the way we're going to think about this is through the lens of potential outcomes with a slight twist. So we're going to think of each entry in this matrix of users and combinations as, say, a noisy potential outcome. Okay, so for yn pi represents the noisy potential outcome for user n under the combination of movies indexed by pi. Okay, and we're going to think of it as we traditionally do in matrix completion, as its expectation plus some noise, right? So this is the thing I'd like to know is, what was the expected potential outcome for that user, for that combination. If we, let's say, repeated let's say they came to the platform again and again and again, what is their average rating? Right? And so we think of this epsilon and pi as the entry-specific noise that we are thinking of as idiosyncratic noise that we don't want to think about. Okay. So what is the goal? The goal is to estimate the expected potential outcome for every user under every combination, right? So n times 2 to the p expected potential outcomes. That is the goal of this, of what we're doing here. Okay. So let's think of potential one way, because so this is the part, the next few slides, where it's the most, let's say, technical. So bear with me. In the end of it, I'll ask people for questions that they might have. So let's say you are in this setting. Let's say you have combination pi, and let's say there's p movies in total. So one way of representing this, let's just say the total number of movies is 5, and any one combination is movie 1 and 2. One way of representing this combination is through a Boolean vector. A Boolean vector is a vector of 1s and -1s or 1s and 0s. They're equivalent. So in this particular case, there would be 1, 1, -1, -1, -1, because the first 2 movies are selected in this combination, and the next 3 movies are not. Okay, so that's one way of representing a combination, is through a Boolean vector, right? And so each combination pi, which is every combination, corresponds to a unique binary vector. Okay, so it corresponds to a unique binary vector in -1, 1 to the p. Okay, and now one way of thinking about this expected potential outcome is as a function, and particularly a Boolean function. A Boolean function is something that takes in a vector of Boolean vectors, something like this, -1, 1, whatever, and outputs a real number. So such functions that take in Boolean vectors and output a real number are called Boolean functions. And you can think of this function expectation yn dot as a Boolean function, because it takes in the combination. You can think of combination as a Boolean vector, and outputs a real number, which is your expected rating for that combination for that user. Right? So there's a separate Boolean function for every user n. Okay. So that's basically it. So you can think of converting the combination into a Boolean vector, and then this function expectation yn dot takes a Boolean vector and outputs a real number, which is expectation yn pi. Okay. So the main takeaway here is that potential outcomes in this combinatorial setting can be expressed as Boolean functions, and that gives us a lot of things, which is it has a lot of implications. Now, before we get into the implications, another thing to think about is that even rankings can be thought of as Boolean functions, right? A lot of times, let's say if you're going to Google the ads you see, there's a ranking of them that you see, right? So many times the intervention is not just a combination, but it could be a ranking, and that can be thought of as a permutation, right? For even in the Netflix setting, which movie you see first, which movie you see second or third in this when you go to the home page has an implication, right? So one way you can think about it is that permutations can also be expressed as binary vectors, right? So let's say I have in particular, you can think of, let's say I have p movies, you come up with a vector that is p square long, and each of those indexes tell you whether movie I and J are swapped according to a canonical ranking. Okay, so you don't have to understand the details, but the point is that any ranking over p items can be expressed as a Boolean vector of dimension p choose 2, basically p square length. Okay. So it's -1, 1 to p choose 2, right? Because what you're looking at is, did you swap those particular movies or not in that ranking, in that permutation? Okay. So potential outcomes over permutations can also be expressed as functions over binary vectors. Okay. So whether you have a combination or a permutation, you can express this as a Boolean vector. The thing that changes is that with permutations, the length of the Boolean vector is going to be significantly longer. It's going to be p choose 2 versus just p. Okay. So how do we express these Boolean functions? So now what we've done is we've said, okay, I'm going to express my outcomes, but potential outcomes, expected potential outcomes as Boolean functions. Now, what is that bias? So what are some representations that you can do for a Boolean function? The most naive one that you might think about is a one-hot representation, which is that this function expectation y(n) dot can be expressed as essentially a one-hot encoding over the various values it can take. Right? This is the trivial, in some sense, representation of it. So the sum over all combinations, and you just do an indicator of whether that combination is selected. Okay. So the problem is that one-hot representation does not encode the sparsity that might exist. So let's just say that your rating, right, only matters based on one item, one movie. Okay. So I'm a user. I only care about Harry Potter 1, the first Harry Potter, whether it was in the thing that was recommended to me, and if it wasn't, I just don't watch anything. Right. So I have a very, very simple preference that of my potential outcome is really simple, because all that matters is whether the first Harry Potter was in it or it wasn't. Now, the problem is that if you try to represent this in this particular representation, this one-hot representation, you still need all 2 to the p basis vectors, which are this indicator values, to represent this function. Right. So it's not somehow capturing the fundamental sparsity that exists in the fact that my combinations are not very complex. Right. So that's really the problem. So is there a more compact representation that we can exploit? There's a really nice study I believe that has been particularly used in theoretical computer science, called the Fourier analysis of Boolean functions. And that's what we're going to use here to really very cleanly exploit the sparsity that might exist across people's preferences, across different combinations. Right. So the basic idea is that any Boolean function can be expressed as a Fourier series. So let's define what a Fourier series is. So let's say I give you a subset S of P, of the P items. So here's the Fourier basis. So this X of S, or chi of S, is considered a Fourier characteristic. And what it does is the following. So what you do is this kind of interesting, somewhat non-intuitive operation, which is you look at the product of the one-hot encoding for just the subset S. Right. So let's run it through an example. So let's say I have P movies. Okay. 1, 2, 3, 4, 5. And let's say I want to do and there's one combination called 1, 2. Okay. So there's one combination which just picks out the elements 1, 2. So what is the Boolean representation for this? It's 1, 1, -1, -1, -1. Right. That's clear. Now, let's say I want to know the Fourier characteristic for the set 1, 2, 3. Okay. So what is the Fourier characteristic for the set 1, 2, 3 when I applied this combination pi 1, 2? It's 1 times 1 times -1. Okay, so it's -1. Right, so so this is probably the most complex mathematical slide. So I'm going to run through it again, and then a slide I'll just stop for questions. Okay, so Fourier character is, think of it as that Boolean functions can be represented through a Fourier basis, and I'm going to define the Fourier basis. The Fourier basis, a single element of the Fourier basis is chi S. What it does is that it's a function. So it takes a combination and it outputs a number, which is either 1 or -1. The way it does that is through the following operation. Okay, so you have 1, 2, 3, 4, 5. Convert that. So that's my set of movies. Take a combination 1, 2 that can be expressed as the Boolean vector 1, 1, -1, -1, -1. And then the Fourier character chi S that is defined over the set combination 1, 2, 3. This is what happens when you apply the function pi into it. Right? It just looks at the subset. So it looks at 1, 1, -1, -1, -1. It looks at the subset that it cares about. And this subset it cares about 1, 2, 3. And then applies 1 times -1 to it. Okay. So this is this somewhat strange basis, but it's a very powerful basis. And the one key thing is that when you took at any 2 of these Fourier characteristics, let's say chi S and chi S prime, which are 2 Fourier characters associated with the combinations, they turn out to be orthonormal. Okay, so that's a really nice fact. So what that means is that they're a basis. because there's 2 to the p such Fourier characters. There's a Fourier character associated with every combination. And they turn out to be orthonormal in the sense that when you take the inner product of these 2 things, which is expressed in this way, they're only 1 if those 2 characters are the same. Those 2 Fourier characteristics are the same. Okay. So maybe let me just stop here for some questions of the INE. Okay. So because we have this beautiful representation called the Fourier analysis of Boolean functions, where you can represent any Boolean functions in this particular basis, we have the following representation, which is that expectation of y and pi, which is your expected potential outcome, can be expressed as a linear combination of in this basis. Okay. And there's something really nice that comes out of this. So we can follow the math offline, but the basic implication of what's happened is the following, which is that you can represent this Fourier combination, which is expectation of y and pi. It can be represented as an inner product of alpha n, which is the linear coefficients associated with this basis, and the basis itself. And the nice thing here is you can see that the n, the dependency on n and the dependency on pi have now separated, right? Very much like what we are used to in matrix completion or in low rank settings is that there's a separate basis vector for the row, there's a separate basis vector for the column. The same thing kind of shows up here, is that when you're trying to represent a potential outcome, y and pi, expectation y and pi, you have this linear representation in terms of alpha n and chi pi, where the alpha n and the Fourier coefficients index to n, they're not indexed by the combination. And there's another basis vector that is indexed to the combination. And this is the beautiful thing that we're going to be exploiting through this talk. Okay. So this is, I would say, the end of the math, like truly like somewhat dense part of the talk. So if there's any questions, very happy to take them now.
Sorry, I have one quick question.
Please.
Okay. So is there an intuitive interpretation for these alpha n? So is there a reason I would want to do testing on those, for example?
So these alpha n, this representation always exists because it's a basis. And then we'll talk about the only thing we're going to, so in some sense that the existence is always there. Now the question is what kinds of properties do you want to put on the alpha n, right? And we're going to talk about that. So we're going to talk about what different kinds of structure you would want to generally put on combinations of interventions. What does that imply on alpha n? So we'll talk about that. And so when I get there, please ask the question again if I don't answer it. Yeah.
That's great. Thank you.
So here's, yeah, go ahead, Christina.
Oh, are there other natural bases for Boolean functions as that have been studied, or is Fourier basis the predominantly used one? And particularly, is it significant that you're using a ±1 representation as opposed to a 0-1 representation of the Boolean?
No, I don't. I think it has some mathematical convenience, but it is not a fundamental thing whether it's 1 - 1 or 1 0. Now, if there are other bases so I'll say the following, which is that what we are basically relying on is the sparsity of this alpha n, and we'll show that many things lead to a sparse alpha n. And so it might be the case that there are other ways you want to put structure on your combinations that may not lead to the most sparse representation. So, but I don't know what other bases there might be. Abhinit, you might want to answer it in text if you can think of another one. Perfect. So what is the representation over the one-hot representation? What is the advantage over the one-hot representation of using this Fourier basis? So one nice thing is that let's say we return to the example of only the first movie matters in any combination, right? So the one-hot representation will require 2 to the b basis vectors to represent that. And with the Fourier representation, you only need 1 vector. So your alpha n actually is 1 sparse, which is really nice, right? So it naturally captures the structure in your preferences of combinations to the sparsity of alpha n, right? And that's really what we're going to exploit, right? So the Fourier representation, this alpha n, is what captures the sparsity. And so you can ask the question of what combinatorial structures naturally lead to sparsity. So one example is, say you have this kind of K junta item sparsity where let's say there's only, I am someone who only cares about fantasy films. right? So there's a very small subset of fantasy films, and my preferences only matters on that. I don't care about any other genre. So those would be called a K janta, right? That's a typical thing that's studied in combinatorial, anything to do with combinations of items. And there, the sparsity S, which is the sparsity of your alpha n, can be written as 2 to the K, where K is the size of your janta. Another one, which is typically studied especially in design of factorial experiments, is where, let's say, there's only pairwise interactions that matter, right? So all of your items matter, but the level of interaction is somehow bounded. In that case, your sparsity would be something like p squared, right? Where instead of it being p squared or p cubed, depends on the level of interactions you want to allow between different items, right? P square is probably, pairwise interactions is probably the most common one studied in factorial design. And so in that case, it would lead to the sparsity parameter S being p squared. Okay, so you can see the difference of kind. So expectation of y and pi in the K janta set, did you look over all combinations in that K that matter? And then for the other one, you'd look at all S, which is where the cardinality is less than 2. Right? In both settings, the sparsity is significantly less than 2 to the p. Okay. So what are some current approaches to exploit sparsity? So one way is we just put sparsity on the different units, and we think of the different units living in different universes. And we just don't care about the fact that there's structure across different users. There's only structure across different combinations. There's a lot of lovely work that's been done. Two things that we built upon is one is by Nigaban and Shah, which studies the lasso, and then by Sirkanis and Zampatakis that study regression trees or CART. Right. And so what they do there is think of it as running essentially, let's say we look at what Nigaban and Shah did, is they run the lasso, which is, let's say for every user, they run a separate lasso, where for a particular user, they run a supervised learning algorithm between what they do observe, let's say, combination, let's say the first two combinations here for Suhas, the 2 stars, they run a regression between the observed Fourier characters, because you know that basis, across those outcomes. And when you run that lasso, you'll get an alpha hat, and then you can use that alpha hat to impute the missing outcomes for that particular user. And you can repeat in some sense, right? So you learn this alpha hat and you repeat it for any unobserved items. And you can repeat this process across every different user. Now, the problem is when you only exploit sparsity and you run a separate regression across different users, the number of parameters you have to estimate goes down from n times 2 to the p to n times s, right? Because you still have to run this regression separately for every different user, right? And so it can still be quite large. It can still be like n times 2 to the k, which could be prohibitively large. The question is, can we improve upon this? Can we get what we traditionally get from matrix completion, which is like n plus s, which we'll find is actually the natural lower bound in terms of the number of parameters you have, right? So the problem with this kind of lasso-based procedure is that it does not exploit cross-sectional structure. The fact that users could be similar, that is not being exploited by this algorithm. So is there a way to do that? So matrix completion is a really nice way of doing that, right? The whole thesis of matrix completion is that users kind of behave similarly. That idea has been used in causal inference in many different ways, synthetic control, difference in differences. Fundamentally, they rely on this fact, one way or the other, is that different users look similar to each other, one way or the other. And matrix completion is a different lens on this. So what does low rank matrix completion say? It says that a few factors explain most of your data. In particular, you can express it in terms of a low rank U and a V. Right, so that's a low rank approximation. There's a ton of work being done here, and I won't be able to do it justice here. But so what is the limitations of low rank matrix completion? Is that the number of samples you need to observe to actually use low rank matrix completion scales as n plus 2 to the p. So that multiplication between n times s has gone away, but you still have this prohibitively large dependence on p, this exponential dependence on p, which would make it not work. And obviously, as we talked about, in real life, most columns you'll have no observations at all, right? So it doesn't exploit the combinatorial structure that different combinations have structure that you can exploit as well, right? So the question is, can we now efficiently estimate all n times 2 to the pre-parameters by sharing information across both units and combinations? That's what we're going to try to study in this. Okay, so can we explore the structure of both the lasso and matrix completion together? So this is the model. So what we assume is that one is that the matrix is low rank. So the rank of this matrix is R, which is a lot less than n and 2p. And the second thing is that the matrix of Fourier coefficients, right? Let's just put it as cal A, right? Which I take all the alpha n's and just stack it into a matrix. I'm going to say that's row-wise sparse. right? So for each person, they have a reasonably simple notion of complexity of over combinations. So row-wise is sparsity, and then the matrix of expected potential outcomes is low rank. Those are the two key modeling assumptions we're making, which is low rank plus row-wise sparsity. And one thing that actually you get is that you can write, because of this this particular representation here, right? Yn pi equals to alpha n comma chi pi plus epsilon pi. You can actually represent this matrix of ratings as a product of two matrices, which is the matrix of Fourier coefficients and the matrix of Fourier characters. Okay, and now because the matrix of Fourier characteristics is in orthonormal basis, is full rank. So what it implies is that if you apply low rankness on the ratings, it actually implies that the matrix of Fourier coefficients is low rank as well. Right? So fundamentally, all of the assumptions that we're making are on this matrix of Fourier coefficients. That it is in particular row-wise sparse and matrix-wise low rank. Okay, and that's fundamentally the main modeling assumption that's made here. That I think we're only beginning the studying the implication of this. I think this kind of structure where you put row-wise structure and matrix-wise structure, I think there's lots of interesting implications of this that can be studied in different settings outside this as well. Okay, so now let's talk about the algorithm, synthetic combinations. It's pretty natural, so I'll be somewhat quick about it given time. So again, in this setting, most combinations are unobserved, right? Because people haven't rated most people haven't rated most combinations, right? And so what we assume in this setting is that there is a donor set, which is that there's some set of users. The key assumption we're making on the observation pattern is that there's some users that have rated a larger number of movies than most other users. We call them like power users. And what we found in real world application, that this is the case, that there are some users who tend to be highly engaged with the platform, while most users, let's say, have an average level of engagement with the platform, right? And so what that means for these donor set is that they have rated a sufficient number of movies, right? And we'll assume this for this algorithm. And in the paper, we provide a data-driven way of figuring out who your donor set should be. Okay. So there's two steps to synthetic combination. The first step is horizontal regression, which is that for every donor unit, you use lasso on them to learn those Fourier coefficients for them, right? So you run the lasso and say y pi u, you learn that with the Fourier characteristics which you observe. It's just a simple supervised learning problem like running lasso. And then one thing I'll note is that you can replace lasso with any estimator that adapts to sparsity, like CART or even a deep learning method, what have you. And once you do that, once you've learned the alpha hat, you just apply that for every combination you haven't observed, even the combinations you have observed, because you'll have a less noisy imputation, right? So you apply this alpha hat u, which is the learned Fourier coefficient for every Fourier character, and you have now an estimate for every combination in every donor unit. Okay, so then you can apply this across all donor units. And so now you basically have filled out that part of the matrix. Okay, now with step 2, what you do is that now let's say for a user that's not in your donor set, they've rated a far less set of movies. What do you do for them? You essentially so you look at the observed outcomes for that particular user, and you run a regression between that user along with all of the observed ratings for the donor set. Okay, so this should hopefully look a lot like, say, synthetic controls, where you essentially are running this regression between the observed outcomes for your target user or your targets along with everyone else that was under control. It's a similar kind of idea. The particular algorithm we use here is principal component regression. I'm sure there's many other algorithms that could be used. We use PCR because it naturally exploits the low rank structure, right? The assumption that is being made as you want to transfer impute outcomes for a non-donor set is that there's some low rank structures. So some combination of the donor set outcomes looks like my target user, right? That's what we want. And low rankness is a natural way of doing that. And so PCR is a way of exploiting that low rank structure, right? So you basically run PCR to get the coefficients that express a target user as some linear combination of the donor users. And then you just basically apply that, right? And that's it. Right, so it's a really simple procedure. So the first is horizontal regression. So you run lasso on all the donor set. The donor set can be picked in a data-driven way. Once you've imputed the outcomes for all the donor set, then you just basically apply PCR or any type of synthetic control style approach to impute missing outcomes for a donor for any observed outcomes that they have. Okay. And so I'll just note that the key technical challenge here is that when you impute the outcomes for a donor set, right, those outcomes are going to be not perfect, right? And it's not noisy like we traditionally assume in synthetic controls. There is a arbitrary error there in some sense with a bounded norm. And so the technical work to actually work it out requires some innovation. That I'd say that's one of the key technical challenges that we had to kind of work through in this thing, right? So it requires an error and variable analysis of the PCR, but the error and variable analysis without sub-Gaussian noise, but with worst case noise. Okay, so for those of you who are aficionados of high-dimensional error and variable regression, this is a technical side note for you. Okay, so that's the end of the comment of the algorithm. Any questions that people might have? Okay. Cool. So before we get into the theory, I thought maybe I'll just do a quick empirics to show you. So there was a real world case study, which was a generalization of movie lens, where run by Sharma et al., where they basically asked for an online experiment over 800 users rating 30,000 sets of movies, right? And each set contained 5 movies on average, but it had variable size. And users rated on average 45 sets. Over the 30,000 sets. You can see when you start having combinations of things, it really starts blowing up, right? So most of the columns were missing and 99% of the entries were missing. Okay. And so let's ask, do our key assumptions of low rankness and sparsity hold in this setting, right? So indeed, if you just kind of run on the, let's say the subset that's fully observed or mostly observed, you just do SVD on that, you do find that it's highly low rank. Right. So there are a few singular values that tend to explain most of your variance. And then if you actually did the lasso and looked at the sparsity of the estimated Fourier coefficients, only 8.7% of the Fourier coefficients were non-zero. Right? So at least it indicates that there's some level of sparsity in this thing, that there is structure across combinations of movies or items. Now, let's say, how does this method of applying synthetic combinations compare to some standard baselines? So here's how it did. So let's say we applied lasso on every row, right? So there's no notion of a donor set. We just applied lasso row by row. The root mean squared error was 0.8. Now, if you applied different matrix completion methods like soft compute and iterative SD, the general average error for a whole dot set is 0.67. And if you apply synthetic combinations, it drops to 0.55. Right? So there is indeed at least some significant value to be added by exploiting both the row-wise sparsity and the column-wise sparsity and row-wise structure across users. Okay. So just as a sanity check that something nice happens. Okay, so that was a quick empirical study. So one question of when and why do synthetic combinations work? I think the 3 questions, like what are the conditions for lasso to work? What are the conditions for PCR to work? And what kind of confounding is allowed in observational data where you're not running an experiment, right? And then 4th is that, can we come up with an experiment design where these conditions actually hold? Okay, so what are the conditions required for lasso and PCR? For lasso to generalize well, as we start, we need this sparsity. And then the thing you need is that for every particular donor, right, the Fourier coefficients for which you do, the combinations for which you do observe stuff, right, they have some sort of incoherence property that holds. Very typical to the way you'd expect in lasso style analysis, which is that the things you do observe, they're incoherent enough, which means that you can generalize well to unseen combinations. Okay. So in particular, the set of things they observe is rich enough, the column span is rich enough that you can actually generalize well to unobserved outcomes for those particular donor unities. And then for PCR, obviously it's the rank being low. And then the second thing you need is this column span inclusion. So a very similar thing, which is that for the combinations where you do observe for a given user, right, for the target user, those columns are rich enough so you can impute to an unobserved user, unobserved combination for that particular user. Right. So again, these subspace inclusion type assumptions pretty much always show up when you try to do this kind of high dimensional regression. And so it's pretty traditional, pretty standard with what you would need is that the donor outcomes are rich enough so that you can impute and generalize to unobserved combination. Okay. And then what kind of assumptions do you need for observational setting? So let's say you have the classic selection observables, you have something, this is the type of DAG you would have, right? Which is that the observed characters affect both the treatment and the potential outcomes, but then the epsilon, which is the remaining residual noise, is independent of the treatment condition on these outcomes. And similar things show up in low rank in this world of causal matrix completion by Athey and Callas and various other people, where rather than selection observables, you have selection on the latent factors, right? In this world, what we have is something similar, which is selection on unobserved Fourier coefficients, right? So that matrix of Fourier coefficients, that should be enough to explain the treatment assignments, or conditional on those Fourier coefficients, the potential outcomes become independent treatment assignments. Okay. So in putting it all together, when does synthetic combinations work? I'd say, so the first assumption is around the sparsity of the Fourier coefficients. The second one is that the matrix of Fourier coefficients has low rank. So that's, I'd say, the key first modeling assumption. The second one is this Fourier characteristic incoherence, right? So you can generalize, the lasso generalizes. And this third one is subspace inclusion, so that the PCR generalizes, right? And so both the Fourier characteristic and subspace inclusion can be tested for, right? There's an easy data-driven way to test both assumption 2 and 3. The first one is a modeling assumption, but at least you can kind of test for when it doesn't hold by looking at the type of study we did in the Netflix challenge. And the selection for coefficients is a sadly somewhat unverifiable one. And I think that kind of problem always shows up when you do causal inference. Okay, any questions here? I'd say this is the key assumptions that are made. Okay, please do ask along the way if needed. So what is the sample complexity by applying synthetic combinations under those 4 assumptions? So, okay, so let's say you have lasso. Let's say it exploits sparsity, but it doesn't exploit the low rank. The sample complexity is n times s squared p. Now, if you have matrix completion, the sample complexity scales like n plus 2 to the p, right? So you've gotten rid of the, in the first one, you've gotten rid of the exponential dependence on p. In matrix completion, you still have the exponential dependence on p, but at least the n and the 2 to the p are no longer multiplicative. Now, with synthetic combinations, the nice thing is you have the best of both worlds because you've made more assumptions, which is you have n plus s squared p, right? So the exponential dependence on p has gone away and is no longer multiplicative with n, right? And the sample complexity lower bound is something like this, which is n plus s, right? And so there's some work that can be done to actually improve upon the results that we have. The one thing I'll note is that if it's a k-junta and you use something like CART, then the p can be removed. The second thing I'll say is that the s square shows up because we prove our results all in the infinity norm. So it's the max error over any entry in your matrix. If you care about a more average sense of error like Frobenius norm, then I believe there's a way to make this into n plus s. Okay. And the paper, we also do work around proving not just this kind of consistency, but also an asymptotic normality result. But I'll leave that to be read in the paper itself. So the point is that by adding more assumptions, you hope you get more. And at least here you can see that by adding both the sparsity assumption and the low rank assumption, you do get both by exploiting that. Okay. The last point I'll have is around experiment design. So let's say I could design an experiment. Let's say I'm not in the world of recommendation systems, but I'm in the world of, say, gene knockouts, where I can decide which genes I'm knocking out for different individuals. Or I'm in the world of, say, machine learning, where I have many different thousands. If you're on Hugging Face or something, you have thousands of different models, and I want to know for each different model which set of features would be best for them. Right? How do I do this at scale? How do I come up with an experiment? So here's one experiment design that works. So let's say this is one way to think about it as a matrix. So rows are the different machine learning models, different individuals, whatever. And the columns are different combinations, like different combinations of features, different combinations of genes you're knocking out, etc. So what you do is you randomly select a subset of users or rows, right, which scales something like R. And those are your donor sets. And for that donor set, you sample something like R squared times S squared times P combinations. Okay. And then for the remaining users, you sample R to the 4 combinations. Okay, so let's say you have this L-shaped. So point is, you take your individuals and you take your combinations, you put them in a matrix, and you sample an L like this. okay, where the base of the L is something like R squared times S squared times P. That's the number of combinations for the power users. For the non-power users, you have R to the 4, and the number of power users is R. Okay, if you randomly sample something like this, right? So one way of thinking about this is that you're randomizing. In matrix completion, we think about randomization by entries, right? When you look at traditional matrix completion, when it was originally came out by like Candice et al., what they were doing is to say, just randomly sample entries in your matrix, and with high probability, there's enough signal there that you can impute every missing value, right? What we're saying is that rather than doing this randomization entry-wise, you do this randomization row-wise and column-wise. And if you do this randomization row-wise and column-wise, you get this L shape show up. Okay. And then with this, you can actually ensure with high probability the various subspace inclusion properties hold with high probability. Okay, that you need to transfer for the subspace inclusions for both PCR and lasso hold with high probability in the setting. And with this level of number of entries that you do observe, you can recover with high probability entry-wise guarantees with n plus s squared p parameters. Okay, so here's one way of thinking about experiment design that you could run. And with that, I'll end. Thank you very much for listening, and any questions you have, I'd love to answer. And Christina, please take it away.
Thanks for a very nice talk. Can I ask one very quick question before you go to? So computationally, how do you do this actually? So because, for example, the original lasso that you're running, you have, if you do the full basis expansion, you have 2 to the power of p many features, right? So you're probably not doing that. So like, are there some other trick, or like how are you doing things in practice?
Yeah, maybe Abhinav, you want to take that, or on lasso, how do you do it with 2 to the p?
Yeah, there are a few ways you can do it. So one, you can say that I only allow some low degree interactions. And if so, then you limit your basis. The other things you can do is like apply a nonlinear method like CART, which will sort of learn the interactions that are important in the first place. And lastly, there's a line of work on sort of sparse Fourier transforms that allow you to compute things in a computationally efficient manner. So I think what's important here is that the lasso is one approach of doing this horizontal regression, but it can be replaced with any sort of regression algorithm that can exploit sparsity. And CART and sparse Fourier transforms are 2 examples of those.
Sounds great. Thanks. Okay. Yeah. So without further ado, Christina, please take us away.
I think you're on mute, Christina.
Okay, great. This is better. All right. So, so I guess I'll also give my view of the overview of the paper. So, the setup of this paper is in a setting where we have combinatorial interventions. So say there are P interventions, and we want to understand the outcome under all different subsets. So there's 2 to the P subsets. So again, you can think of the data as being represented as this as observed entries in this matrix, where there are n units. For every unit, there's a different subset of these combinations where under which the outcomes are observed. And the goal is to estimate the outcomes under every combination. Again, the challenge here is that 2 to the p is exponential in p, and so this matrix is extremely short and wide and extremely sparse. And the key idea again exploits 2 types of model structure. The first kind of model structure is that for every given unit, the outcome function is sparse in the Fourier basis, and in particular, at most there are S with being the sparsity parameter, S non-zero Fourier coefficients amongst these 2 to the p basis elements. So it allows you to write your outcome function as again a linear functional of in product of these coefficients alpha and these basis elements chi, and where the sparsity of this alpha parameter is bounded by S, and epsilon is this mean zero noise. Again, this task of estimating functions under sparsity is actually well studied. So one particularly widely used method is lasso, where you just minimize the squared error with respect to a L1 regularizer, and this L1 regularizer encourages sparsity in these alphas. And the lasso has sample complexity S squared P, again, if you simply use lasso out of the box for each of these n units, you'd have to pay linear in n sample complexity for again n times s squared p to be able to estimate the model. So the idea is that what their method exploits is that there's a set of donor units for which the set of donor units have a lot of observed observations. A lot meaning enough to sufficient entries that you can actually use lasso to predict the other entries. So here you can see, say, the bottom 3 rows are units for which there's a lot of observed outcomes, and then you use those observed outcomes to estimate the remaining units. And the technical assumption here is that, you know, it again inherits all the properties of lasso, so you'll need to have the same properties that lasso needs to be able to estimate, in particular, the incoherence of the Fourier characteristics for these observed combinations associated to donor units, meaning that the observed combinations are kind of sufficiently representative enough, so you can recover the correct alpha. Now, the second key model structure that the approach uses is that the outcome matrix has rank R meaning that this matrix can be decomposed as a product of a tall matrix and a wide matrix. So if I have an n by m matrix, I can write it as a product of an n by r matrix and an r by m matrix, where r is the rank. It also means that any row can be written as a linear combination of other rows. And in general, this matrix complexity completion has sample complexity that is linear in n plus m, because as you can see, the degrees of freedom of the model is linear in n plus m. And the approach that they use in this work is principal component regression. It's just one way to do matrix completion. And I would say the key unit of computation is identifying, say, a setting where if I want to observe this pink entry in the upper right, if I observe a submatrix that is fully observed, then I can estimate this pink entry in the right by taking this vector A multiplied by an estimate of B inverse, and then this vector C. So this A, B inverse is what they refer to as the weights. This is the weights to tell you, how do I recover this pink entry as a linear combination of the entries in this vector C. And this B inverse is approximated using singular value thresholding. And so now when you put it together, you can take, after you do your first stage and use your donor units to estimate all of the outcomes for the donor units with lasso. Then for a particular target unit, if I want to estimate this pink entry here, I again observe the same kind of motif that we saw earlier. So I look for this submatrix here, where in particular this vector A is going to be the set of all observed entries for the target, and then B and C are going to be outcomes either observed or estimated for my donor units. And in particular, it relies on the fact that because I was able to estimate all the outcomes for my donor units, you can always find a submatrix like this. So then you can also get the technical assumptions you need to get guarantees on the PCR will also rely on the technical conditions that that PCR needs. So in particular, you need a balanced spectrum of your donor units. You need these horizontal span inclusion, linear span inclusion, subspace inclusion. Again, these are all properties that guarantee the missing entry is within the row span or the column span of the entries that you're predicting it from. And so the paper shows identifiability, finite sample consistency, and asymptotic normality. And they achieve a sample complexity that does scale linearly in this n, meaning the number of units, plus the complexity for a single lasso, s squared p, and then it's polynomial in the rank. And this novelty is that I think the technical novelty and the modeling novelty is combining the low rank structure with functional structure. I think low rank matrix completion has been studied for a while, but I have not seen other works that have combined the low rank structure along with other kinds of constraints on the function class. So that's that was kind of a very interesting new technique. And the challenge, as Anish mentioned, was that you have to deal with a very different kinds of noise that arise from the errors in the lasso in stage 1 when you're analyzing the PCR, principal component regression, in stage 2. And so that itself, I think I would say also has very interesting implications towards more general analysis of PCR and applications of PCR in other settings when you have different types of noise. I think the important practical consideration one would need to think carefully through when you're applying a method like this is understanding this existence of a donor set and what are scenarios in which you do have a donor set or you may not. And in particular, it suggests this imbalance in the observed outcomes. In particular, donor set, in stage 1, you can think of the donor set as being ones in which you have a lot more outcomes observed, and so you're relying on this set of representative units that are your donor set that have significantly more combinations that are observed. And the experimental design that Anish suggested is one in which these representative units are randomly sampled in order to guarantee, or with high probability, that they will be representative, and also that these combinations are also randomly sampled, again, to make sure that you satisfy the conditions you need for lasso. In the observational settings, I think the challenge could be that even in settings when you do have a significant, a small population of users that are rating a significantly large population of the movies, it could also be biased towards users with a certain type of Fourier coefficients in some sense, right? So, their work does allow for selection on this latent factors, these Fourier coefficients, but if the selection is such that the donor units, who are again your power users, are actually a subspace within your Fourier coefficients, then it may not satisfy that linear span inclusion. So in some sense, you still need to think about, is my power users that I'm going to estimate from, are they, even though they could be a biased set of my population, are they still representative enough that they still span the population in terms of represent all different kinds? So I think that's an important practical consideration. A few interesting questions and extensions I have for Anish and Abhinit is that this, what they actually mentioned, this first point, is that the horizontal regression in step 1 of the algorithm actually is quite general. So they do extra extension to CART. I think it was not obvious to me whether the particular choice of Fourier basis matters, in particular if I had any other basis. So if someone gave me a basis and told me it was sparse in that, presumably you could actually use that as well. So in particular, it would be amenable to maybe even beyond settings of combinatorial intervention. So in particular, this is a setting, Fourier basis makes a lot of sense because you're looking at Boolean functions. But if I had a lot of interventions, not necessarily combinatorial, but a lot of interventions, and I had maybe side information associated to the intervention, then I could impose some function class that relates the features of my intervention to the outcomes. And then again, you could use any kind of ML or regression step in this step 1 of the algorithm to again extend the results they have to this broader setting. So I think, and it was not clear to me also if the basis needed to be orthogonal. If it wasn't orthogonal, but it still had sparsity. I'm not sure if the orthogonal came in the incoherence part of it, but I think there would be some work needed to think through what does the implications on the incoherence mean about extensions to beyond Fourier basis. Also, I was curious about the implications towards network interference, because I could think of these combinatorial interventions. They're also could be used to represent that an individual's outcome is a function of the combination of its neighbors that are treated. And so if I have a very large neighborhood, then perhaps actually one would want to use something like sparsity as the paper exploits here, to actually fully say that if I could observe observations of a user under different patterns of treatment, I could estimate the entire outcome function under any neighborhood of treatment. So I think there's maybe the difference is there's an additional dependence in terms of the treatments are correlated. I don't know how big of a difference that would make in terms of the results you have. And then the Fourier basis actually is also very similar to the low order polynomial models that have been looked at in the network interference setting, although the Fourier basis with the ±1 is measuring things like parity, but the low order polynomials are, on 0, 1. And so it's measuring something more like the presence of a set being treated or not. So I don't know how similar it is or not. And that was something that I was wondering. And then the last question was, this experimental design, again, it required this imbalance in the assignment of treatment, so the intervention. So if we had a setting in which there was a balance constraint that maybe every user actually had a budget of time, and so I am not able to have a significant imbalance, is there any way that you guys thought about where one could explore simultaneously exploiting low rank and sparsity instead of like a two-phase approach, but a way that you could do it together if you didn't have enough, if you didn't have power users? So that's all I have.
Thanks for the very nice discussion. Anish or Abhinit, feel free to respond.
Yeah, I think first, Christina, thank you for super thoughtful, as always, take on a paper. I think the couple of things you said that really resonate with me is first, we had this particular basis, Fourier basis, then we applied the lasso for the horizontal regression, but potentially they can be plugged in and out in terms of a different basis that you have and a different kind of regression algorithm. And so potentially one extension is just generalize all of this, so you can plug and play whatever developments are happening in any field of ML. Can you just plug and play it here? And I think the idea that you had, the same thing kind of applies to the second step, which is all you really need is that A, B, C and question mark, right? And any algorithm that can work with A, B, C question mark should be applicable, right? So so whenever you don't have enough observations in one direction, as long as you can find A, B, C question mark, any algorithm that works for that should work. And nearest neighbor methods are particularly good for that kind of sparsity pattern. And so potentially and the synthetic controls literature. And so again, there's a generalization present there that I think can be worked out and probably should. I think the other thing that what you said made me think about was that, so we can have this Fourier basis or some featureization of the interventions. You could probably also have a featureization of the users, right? A lot of times it's not individual users, it could be cohorts of users, and a cohort could be defined again by Booleans, right? Like, are you above this age or not? Are you live in this geographic location or not? So a lot of times, I'd say in practice, you probably have a Boolean representation for some subset of your features for both the columns and the rows. And so how do you think about all of that in an elegant way, I think remains an open question. And maybe that is potentially one way of getting away with this idea of a donor set, and making it more symmetric, I think could be an interesting thing to think about, to go away from this asymmetry across both sides. So I think those are all important things to study, and I think your discussion has made me now, or hopefully all of us, think about it more in a more clear way. Yeah. I don't know, Abhinit, do you have anything to add?
No, I guess for the last question, there's a whole line of work on sparse reduced rank regression, which kind of does this both on the design matrix. They assume both low rank and sparsity, or like row-wise sparsity and low rankness. And I think that would actually allow you to sample a uniform number of combinations per, say, user. So you don't need to have this imbalance design. I think where the imbalance is useful is that for a new user coming in, you have to sample a lot less to learn their combinations. So it's I think it's useful for like just introducing a new user to your recommendation platform.
Mm-hmm.
And lastly, I think the network interference is like a very natural, there's so much work being done in causal inference around network interference. And I think this this idea of thinking about it through Booleans is an interesting one, and I think there's a bridge to be made there in a more cohesive way over time. Yeah.
Awesome. Thank you. I think
you.
I think it's time to wrap up. So first, thank you so much, Anish, Christina, and Abhinet for a very nice seminar today. Yeah, just looking forward. Next week, we're going to have a young researcher seminar. So we're going to have two speakers, Bijan Mazaheri from MIT and Harvard, who will talk about synthetic potential outcomes and the hierarchy of causal identifiability, and Philip Faller from Karlsruhe Institute of Technology, who will talk about self-compatibility, evaluating causal discovery without ground truth. Yeah, thank you all for coming. I hope you have a great week, and see you next time.
Thank you.